to our AI Study Jam session. And as you can notice, we update name from Machine Learning Study Jam. For now, it's AI Study Jam. So it's great to see you all again. The week 3 of our AI Study Jam will be about diving into the exciting world of deep learning and computer vision. But before we start, I'd like to mention that it's a friendly and inclusive space. So let's encourage each other and lift one another up. Negative comments, jokes, or behaviors that put others down have no place here. Please maintain professional and friendly attitude. If something doesn't feel right, let the host know during the event on QA part or reach out via email. We are here to make sure everyone feels comfortable and, of course, included. This event session will be recorded. So, but first of all, let's quickly recap the intermediate machine learning and feature engineering concepts you explored in the Kaggle courses. Remember, feature engineering is crucial for improving model performance. This course, Intermediate Machine Learning, addresses the challenges of real-world data, including missing values, non-numeric data, and data leakage. It provides techniques to enhance machine learning model quality. The course welcomes us with prior machine learning background, aiming to elevate our model performance. Key areas of focus include meaning real-world data complexities, streamlining workflows with pipelines, ensuring robust model evaluation throughout cross-validation. Also, XGBoost was introduced as a powerful algorithm, and preventing data leakage was emphasized as a crucial practice. Practical application occurs throughout hands-on exercises using the house prices competition dataset involving 79 explanatory variables to predict more prices. Progress was measured via leaderboard submission, and the housing price competition served as a practical platform, allowing us to apply concepts and track our improvement. Missing values were addressed. This challenge in real data sets was explored. In this lesson, 3 approaches to dealing with missing values were learned. The effectiveness of these approaches was then compared on a real-world data set. It was noticed that data can end up with missed values in many ways. For example, a 2-bedroom house won't include a value for the size of a 3rd bedroom. A survey respondent might choose not to share his income. It was emphasized that most machine learning libraries, including scikit-learn, give an error if you try to build a model using data with missing values. Therefore, strategies to handle these missing values were required. The simplest option, dropping columns with missing values, was examined. It was observed that unless most values in the dropped columns are missing, the model loses access to a lot of potentially useful information. An extreme example, a data set with 10,000 rows where one important column is missing, a single entry, was used to illustrate the loss of information. Imputation, which fills in the missing values with some number, was presented. For instance, filling in the mean value along each column was shown. It was explained that while the imputed value won't be exactly right in most cases, It usually leads to more accurate models than dropping the column entirely. An extension to imputation was covered. It was noted that imputed values may be systematically above or below their actual values, or row with missing values may be unique in some other way. In such cases, involved imputing the missing values and adding a new column that shows the location of the imputed entries for each column with missing entries in the original dataset. It was mentioned that this could meaningfully improve the results in some cases, but not in others. The Melbourne housing dataset was used in the example. The model utilized information such as the number of rooms and land size to predict home price. The data loading step was not focused on. Instead, it was assumed that training and validation data were already in X train, X valid, Y train, and Y valid. The data loading step was not focused on. So, the function score dataset was defined to compare different approaches to dealing with missing values, reporting the mean absolute error. Later, we always will use abbreviation MAE from a random forest model. It was concluded that imputing missing values generally yielded better results than dropping columns, especially when missing values were not overly prevalent. In this lesson, we explore the crucial topic of handling categorical variables, a common data type in real-world data set. We learned that these variables, which contain limited numbers of distinct values, require pre-processing before being used in most machine learning models. Also, we cover three primary models: dropping categorical columns, ordinal encoding for variables with a clear order, and one-hot encoding for variables without inherent ranking. Throughout the practical examples of the Melbourne House dataset, we observed how these methods impacted model performance, ultimately concluding that while one-hot encoding generally yields the best result, the optimal approach can vary depending on the data set and the nature of the categorical variables themselves. The key takeaway is the importance of understanding and effectively utilizing categorical data to build robust and accurate machine learning models. Pipelines essentially create a sequence of operations, making your code more organized and efficient. The lesson highlighted that while many data scientists build models without pipelines offer several important benefits. Cleaner code. Pipelines simplify the management of data at each pre-processing state. Fewer bugs. Pipelines reduce the risk of misapplying or forgetting pre-processing steps. Easy to productionize. Pipelines facilitate the transition of models from prototypes to deployable solutions, and more options for model validations. In this case, pipelines enable advanced validation techniques like cross-validation. The Melbourne House dataset was used for demonstrations similar to previous lessons. It was assumed that training and validation data were already loaded into X-train, X-valid, Y-train, and Y-valid. And this lesson demonstrated how to streamline machine learning workflows using pipelines. First, we define preprocessing steps. In the column transformer, bundled numerical imputation and categorical imputation, while one hot encoding into a single preprocessing unit. Next, we defined our model, a random forest regressor. Finally, we created and evaluated a pipeline that combined the preprocessing and modeling steps. And of course, this allowed us to feed and predict with a single line of code, ensuring validation data was consistently preprocessed. We have evaluated the model using mean absolute error. In conclusion, pipelines simplify code, prevent data leakage, and make complex preprocessing more manageable, providing to be essential tools for efficient machine learning. Cross-validation is a technique to assess how well a machine learning model will generalize to an independent data set. It addresses the limitation of a single validation split by dividing the data into k folds. Each fold is used once as a validation set, while the remaining folds train the model. This process provides a more stable and reliable measure of model performance, reducing the impact of random data patterning. We use scikit-learn cross-val score function to automate cross-validation. This function handles the creation of folds, the training of the model on each fold, and the evaluation. The scoring parameter allows us to specify the evaluation metric. When we use negative mean absolute error or negative man. This is because scikit-learn uses a convention where higher scores indicate better performance, and we want to maintain consistency even throughout may itself is a measure of error. Cross-validation is particularly valuable for small data sets, where a single validation split may not accurately represent the data's variability. It reduces the impact of randomness in data patterning, providing a more reliable measure of model quality and improving the model's ability to generalize it to unseen data. While it's beneficial, we must consider the computation cost, especially when working with large data sets. In such case, a single validation set might be sufficient. XGBoost or extreme gradient boosting is a powerful ensemble learning technique for structured data. It builds on the concept of gradient boosting, iteratively adding models to an ensemble to improve prediction accuracy. We'll explore how XGBoost works, its key parameters, and how to optimize it for performance because it's super important and crucial. Gradient boosting is an ensemble method that sequentially adds models to correct errors made by previous models. XGBoost is an optimized version of this technique, known for its speed and performance. It uses gradient descent to minimize a loss function, iteratively improving predictions by focusing on the errors of the current ensemble. XGBoost has several key parameters that significantly impact its performance. And estimators control the numbers of boosting robots. Early shopping crowds allows us to automatically find the optimal number of estimators. Learning rate scales the contribution of each model, affecting both training speed and accuracy. And jobs enables parallel progress processing, speeding up training, or even larger data sets. Tuning these parameters is crucial for achieving optimal performance. AGBoost is a leading library for working with structured data, providing high accuracy when properly tuned. Parameter tuning, especially adjusting the N estimators, early shopping rounds, and learning rate, is essential for achieving optimal performance and avoiding overfitting. By utilizing these techniques, you can build highly accurate and efficient models. Data leakage occurs when training contains information about the target that won't be able during prediction, leading to misleadingly high model performance. And we'll, of course, need to explore target leakage, train test contamination, and how to identify and prevent these issues to ensure reliable models. There are two main types of leakage. Target leakage happens when predictors include data that won't be available at the time of prediction, like using future information to predict the past. Train test confirmation occurs when validation data influences preprocessing steps, leading to over-optimistic model evaluations. Both types compromise the model's ability to generalize to new, unseen data. Detecting leakage involves careful data inspection for suspicious relationship and ensuring proper separation of training and validation data. Using cross-validation and pipelines is crucial for preventing train test contamination. To prevent target leakage, exclude any variables that are updated or created after the target values is determined. By identifying and mitigating these issues, we can build models that perform reliable in real-world scenarios. Future engineering is the process of creating new feature or transforming exciting ones to make data better suites for machine learning models. So the feature engineering course on Kaggle focused on enhancing machine learning model performance throughout strategic data transformation, and it covers techniques to identify and create informative features, including using mutual information to rank future importance, applying mathematical and group transforms, and leveraging unsupervised learning methods like k-means clustering and PCA to discover underlying patterns. Now we will dive deeper into all these terms, abbreviatures. So targeting encoding was introduced as a supervised method to effectively encode categorical features using target variable information. The main goal of feature engineering is to optimize your data for machine learning. This involves improving predictive performance, reducing computational needs, and enhancing the interpretability of results. A key principle is that Features should have a relationship with the target that the model can learn. For example, transforming features to create linear relationship for linear models. To illustrate feature engineering, we use the concrete data set. We first establish a baseline model to measure initial performance. Then we create synthetic features like ratios of ingredients, which are often more predictive than absolute amounts. Adding these ratio features significantly improves our model's performance, demonstrating how feature engineering can expose valuable information to the model. Mutual information is a powerful metric for ranking features based on their relationship with the target variable. It helps us understand which features have the most potential for prediction, especially in data sets with many variables. We'll explore how mutual information works, its benefits, and apply it to 1985 automobiles dataset. Mutual information quantifies how much knowing over variables reduces uncertainty about another. Unlike correlation, it can detect any type of relationship, not just linear ones. It's interpreted in terms of uncertainty reduction or entropy. Essentially, it tells us how much information a feature provides about the target. We apply mutual information to these automobiles dataset using scikit-learn's mutual info regression function. We label encode categorical feature and then calculate MI scores. Visualizing these scores with bar plots help us quickly identify the most informative features. We also use scatter plots, for example, specific relationship like curve weights and price, confirming the insights gained from MI scores. Mutual information scores help us understand the potential of the feature as a predictor. Scores range from 0.0 for independent features to higher values to strongly dependent ones. Remember, MI is a univariate metric, so it doesn't detect interactions between features. The actual usefulness of a feature depends on whether your model can learn the relationship. Visualization and domain knowledge are essential for interpreting and utilizing mutual information effectively. The lesson focused on feature creation with the process of generating new features from existing ones to improve the performance of machine learning models. This involves transforming raw data into more informative representations that better capture the underlying patterns in the data. The lesson covered mathematical transforms, which included applying arithmetic operations to columns, such as creating a stroke ratio from engine data. Data visualization aided in suggesting transformations, such as using logarithm not to normalize scale distribution like wind speed. Count feature were also created by aggregating binary or Boolean feature to represent the presence or absence of certain attributes. Combining features like creating, make, and style revealed valuable interactions. Group transforms aggregate information across rows grouped by a category. For example, calculating average income by state using group by and transform. This technique allowed for the creation of features like frequency encoding. When using training and validation splits, independence was preserved by creating grouped features on the training set and merging them with the validation set. The choice of feature creation techniques was determined by the model's strengths and weaknesses. Linear models benefited from sums and differences, while tree-based models excelled with column features. Normalization and the potential for interaction effects were considered when creating new features. This lesson introduced clustering with k-means as an unsupervised learning technique for feature engineering. Clustering involves assigning data points to groups based on similarity, aiding in the discovery of underlying data structures. When used for feature engineering, cluster labels can simplify complex relationship k-means clustering, which uses straight-line distance, Euclidean distance in other words. The algorithm iteratively assigns points to the nearest centroids and then moves these centroids to minimize distance. Key parameters such as like n clusters, max iter, and n iter were discussed, emphasizing the importance of choosing n clusters throughout hyperparameter tuning. The concept of creating Voronoi tessellation to visualize cluster assignments was also covered. The lesson demonstrates the application of k-means clustering using the California housing dataset. Latitude, longitude, and Med-Inc were used to create economic segments. K-means was applied with n clusters equal to 6, and the resulting cluster labels were added as a categorical feature. Scatter plots visualize the geographic distribution of these clusters, showing distinct segments for higher income coastal areas. Box plots were used to analyze the distribution of net household within each cluster, demonstrating that the clustering effectively separated data points based on median house values. This example highlighted how clustering can transform spatial features into meaningful categorical variables, improving model performance by simplifying complex relationships. Principal components analysis PCA is an unsupervised learning technique that partitions the variation in data, revealing underlying patterns. It transforms original features into principal components, which are linear combinations of the original variables, representing excess of variance. Each component's loading indicates how much each original feature contributes. Principal components analysis is useful for dimensionality reduction, anomaly detection, noise reduction, and decorrelation. The Avalon data set illustrates how Principal component analysis can identify size and shape components from height and diameter. Understanding the explained variance and loadings is crucial for interpreting practical components analysis results. Principal component analysis is typically applied to standardized data to focus on correlation. So, it's useful for dimensionally reduction, as I talk, anomaly detection, noise reduction, and decorrelation. So the lesson demonstrated PCA using 1985 automobiles dataset focusing on highway engine size, uh, horsepower, and curb weight. The data was standardized before applying PCA. The resulting components were analyzed for their loadings and explained variance, revealing a luxury economy axis. Mutual information scores of the components were examined to identify predictive variations. For example, this highlighted a contrast between horsepower and curb weight, suggestions a sport car with vegan definitions. A new ratio feature, sports or vegan, was created to capture these contrasts. This example illustrated how principal components analysis can be used as a descriptive tool to discover meaningful relationship and create new features based on the identified values. So it's sensibly to scale and the importance of handling outliers were also emphasized. Target encoding is a supervised feature engineering technique that encodes categorical features using information from the target variable. It replaces categories with values uh, derived from the target, such as the mean, offering an alternative to one hot or label encoding. Mean encoding, a simple form of target encoding, calculates the average target value for each category. However, this method can lead to issues like overfitting and handling unknown or rare categories. Smoothing techniques such as the M-estimate address these problems by blending the category average with the overall average, reducing the impact of noisy or infrequent categories. The lesson demonstrated target encoding using the movie lens 1M dataset, focusing on the high cardinality zip code feature. A 25% split was created to train the target encoding, ensuring independence and preventing overfitting. The M-estimate encoder from the category encoders package was used with the parameter M set to control noise. The encoded zip code feature was compared to the rating target using distribution plots. The plots revealed that the encoded feature effectively captured user information as its distribution closely mirrored the target distribution. This example highlighted the effectiveness of target encoding for high cardinality features and its ability to reveal informative relationship between categorical features and the target variable. This course emphasized the importance of understanding data throughout domain knowledge and visualization, and provided practical examples to demonstrate how feature engineering can significantly improve model accuracy and robustness. So everyone who did homework and finished these necessary two courses, of course, get two certificates, which now you can receive on Kaggle Learn tab. So, and now let's quickly start with our topic for the next week, deep learning and computer vision. Deep learning is a powerful subset of machine learning. It uses deep neural networks, think complex, multi-layer system to learn intricate patterns. This capability is why it's so transformative, driving breakthrough in areas like image and speech recognition and even natural language understanding. Complementing this, computer vision empowers machine to see and interpret visual data. It's the technology behind self-driving cars, medical image analysis, and countless other applications where visual understanding is crucial. For a deeper look into these fantastic fields, I encourage you to visit our YouTube channel. We've recorded an impressive talk by Shrikanta that provides valuable insights into deep learning and computer vision. It's a resource you won't want to miss. So, and homework for the next week. Kaggle's Introduction to Deep Learning course offers you entry into the world of neural networks and we'll explore the fundamentals of building and training deep learning models, focusing on real-world application. Expect hands-on exercises and clear explanations to get you started with these powerful technologies. Kaggle's computer vision course provides a hands-on introduction to the techniques that enable computers to interpret and understand images. We'll cover essential concepts like image classification, object detection, and feature extraction with a focus on practical applications and coding exercises. This course is designed to equip you with the skills to build and deploy your own computer vision models. So, that brings us to the end of today's session. Thank you all for your participation. Remember to complete your homework on Kaggle, both the Intro to Deep Learning and Computer Vision courses. If you have any questions, feel free to reach out in our community Discord channel. This session was recorded and will be available on our GDG Ahlen YouTube channel later. You can rewatch it at your convenience. Please don't forget to submit the post-event feedback form. Really, your insights help us improve and make future sessions even better. Once again, thank you for joining. We look forward to seeing you in our next session next Sunday. Until then, keep learning, experimenting, and building with AI.